The Probit response model. Probit analysis is used to examine the potency of a stimulus by looking at the effect of an intervention on an aggregate. Now, Probit is not only a model, it's also a type of probability in the same way that Logit is both a model and a probability. Here we're going to look at the Probit procedure. And the Probit procedure allows the Probit and the Logit probability. Right? But a logit probability, log odds, is not the same as a logistic regression. Logistic regressions use the logit probability. So here we're using a Probit model which allows for a Probit or a logit probability, but we're using the Probit model and the Probit probability. So let us get the data. The data is going to be the Probit data set. Now, we may want to establish how much of an effect, in this case, in the model we have here, how much of an insecticide it takes to kill some insects. The effect on the dependent variable must be dichotomous, either a living or a dead insect. And there must be a comparative value between those insects that are living, which are measured as n observed, versus those that are dead, which are n dead. And these are represented as a decimal proportion. The unit of analysis in a Probit analysis is an aggregated sample or group of objects that received the stimulus and either respond to it or died or did not. In other words, they didn't die. Now, the math logic of Probit is that it uses the z-value of a normal curve rather than the raw score. For example, if the response rate is 0.5 or 50%, in the raw score, the z-score is going to be 0. Because recall that a z-score of 0 is at the mean or the average of a bell curve. And because a bell curve's left and right side are symmetrical, if you have a z-score value of 0 and you count the values from the left to the right, you're basically describing half of the insects as dying or half of the subjects receiving the effect. Now, a logit proportion can also be selected, and while the two output values are different, their proportions are nearly constant. You're just dealing with a different way of calculating the shape to calculate a proportion of the total. Now, some definitions that are going to recur. We have total observed. This is the total initial number of individuals in the sample. In other words, the living and the ones that would eventually die. The response frequency is the number of individuals affected by the stimulus in the sample. In other words, those bugs that are killed by the insecticide. And covariates are the independent variables. And of course, you can insert one or more interval level measured stimuli to look at their effects. So let's go ahead and run the Probit regression. So we go to Analyze, Regression, and here to Probit. Okay, so a various number of variables to insert. Response frequency is the dependent variable, and we're going to put in n dead. All right, these are the dependent variable where the effect occurs. The total observed is the population of the insects, those that are living and dead, and those are the n observed. The covariates are the independent variables. In this case, it's the dose of the insecticide. Okay, we're not going to do any transformations yet. We'll look at that later. Under model, we're choosing the Probit distribution. Okay, so here, we're not looking at the model, we're looking at the type of mathematical distribution. In options, on the top right, we have statistics, and we have to ensure that frequencies and fiducial confidence intervals are both selected. We click Continue and OK. So in instances where a subject population suffers a certain natural die-off as a result of old age or other environmental causes, in other words, how long a bug would live without insecticides, that proportion can be inserted into the Probit analysis, or the Probit analysis can attempt to estimate the natural response rate from the data using its own algorithm. And the way that you would do this is, let's going back to the model, you'd go to Analyze, Regression, Probit, and here, under options, you have a natural response rate. And so you could click on calculate from the data, right? And then you click, but we're not going to actually do that because we really have no idea what the natural response rate is, and it's not something that's immediately useful to this analysis. So we're not going to run that. So let's go take a look at some of the outputs. Now again, I'm going to be referring to tables, but know that as SPSS changes, as updates, these tables may change their order. So let's go to table 7 first, which is the Probit transformed responses, this graph here. It was a scatter plot of the log of the dose, which is the independent variable on the x-axis, against Probit, which is the dependent variable on the y-axis. So the relationship should indicate linearity for the Probit to generate unbiased estimates. And in this case it is. If you look at it, you've got this sort of line of interaction between the log of the dose and the proportion of dead bugs. So if not, we have to transform the covariate. Okay, so here's how to transform it. You'd go to Analyze, Regression, Probit, and you would go to Covariates, and here you can do a transformation, a log base 10 or a natural log, to improve its linearity, or at least decrease its curvilinearity. We're not going to do that here because it's not necessary, so we're going to click Cancel. So let's go now to Table 2. All right, this is the convergence information, and it indicates that with the Probit analysis there were 11 iterations in the algorithm of the math, and in fact a optimal solution was found, indicated by this yes. So here we have the parameter estimates in table number 3, and let's look at some of these. We have here the intercept, minus 1.181, and we have the estimate, which is the equivalent of a B coefficient from linear regression at 0.375. Now the dose, which is 0.375 divided by the standard error, 0.024, will give us a value in the form of a z-score of 15.304, and you can then get an estimate of that independent variable to see whether there is a false positive. And there isn't, which means we can generalize findings of this model. So the significance indicates that there is the null hypothesis of no relationship has been falsified. Now we can use these parameter estimates to construct the Probit regression equation, which we're going to look at in a moment. Now the intercept here, the minus 1.181, is the equivalent of the constant, and the estimate here of the dose is the equivalent of the B coefficient in linear regression. So essentially the predicted value, the y hat, is equal to NDED times not the raw score, but the z-score value of the independent variable. So the predicted value is actually the value of the standard normal curve, the z distribution, below which the predicted proportion of the area is found. So if you think about a bell curve and you think about the mean is valued at 0, if you have a -2 or a -3, that indicates how many standard deviations you must go below the mean in order to calculate what proportion of the total shape of the bell curve is included in the value. So think of this as sort of a form of integral calculus. When you look at a bell curve and you want to calculate how much of that bell curve is included as a proportion of the total, you start on the left, and then you include everything on the left. You fill it in as you proceed to the right, and you stop at that value. If that value is a -2, it means 2 standard deviations below the mean. It means everything from the infinite left all the way up to 2 standard deviations below the mean. That part of the bell curve is filled in, and that's the proportion of how many the bugs were killed by a given dose. Okay, so you have to think of it as sort of graphically representing the amount of the bell curve that is fitted in, or that is rather filled in. So the predicted Probit value is equal to the intercept plus the estimate times the value. So the estimate is like the B coefficient. The value is essentially how much of the dose. So the predicted proportion is going to be minus 1.81 in this case, plus 3.75 times the log of the dose value, whether it's 1, 2, 3, or 4. And you're going to find in the notes in the footnotes of the notes how to calculate logs. All right, it's a little bit of an involved procedure, but we're not dealing here with the raw scores. So for the different doses, we have dose 1. Again, we have the intercept plus the estimate times the log of 1, which is going to equal 0, and then you can sort of calculate this out. All of these dependent variables are in the form of a z-score. Okay, so this is minus 1.1 means 1.1 standard deviations below the mean. Minus 1 is 1 standard deviation below the mean. Same here. And minus 0.955 is less than 1 standard deviation below the mean. So, standard deviations are very useful for calculating proportions. And so you'd fill in your bell curve from negative infinity up to this point. And that would be the number of bugs killed, or the proportion of bugs killed out of the total. So you can calculate it for all 4 of these doses. Now the median lethal dose, to find this, it's the dose necessary to kill half of the subjects. This would be the log of the parameter estimate divided by the absolute value of the intercept. The absolute value, of course, is remove the negative symbol. So 0.375 divided by 1.81 is equal to 0.317. And this is the log of the dose for 50% lethal result. Right? You can take a look at the confidence limit chart at 0.5, which is going to create a similar output. 1.181 is the absolute value of the intercept, right? It's just simply removing the negative symbol from that value. So let's proceed to look at the Pearson chi-square result. This is table 4. 1, 2, 3, 4. So it's right here, the chi-square result. So here we have a value of 126.296. The degree of freedom is 42, which indicates the 44 cases minus the 2 estimated parameters, which is both dose and n-dead, which is the independent variable and one of the categories of the dependent variable. So the goodness of fit for a Pearson is the Pearson chi-square correlational statistic. Its interpretation is the opposite of a typical chi-square statistic. Okay, so you have to be ready for this. It would be very useful to carry your notes with you whenever you look at these outputs to make sure you're correctly interpreting this particular application of a test. A significance of less than 0.05 indicates that the model does not fit the data well. A low chi-score value approximating 0 and a high significant value approaching 1 indicates a good fit for the model. So here we have a very low significance, less than 0.05, and so then this indicates that in this case we don't have a very good fit for the model. So if the chi-square significance is low, it could be because the model is not linear, right? We saw the scatter plot below. It could be because the spread of the observed points around the regression line are unequal, which is termed heterogeneous data. In this case, a correction must be applied to the estimated variances for each group of the sample of cases, and this is done automatically by SPSS. So this particular model does not fit this particular set of data that we have well. The dosage just does not correlate strongly with the death of insects, which is what real life is like. You apply a lot of DDT to kill bugs, and after a while the bugs generate immunity, or the bugs only kill certain vulnerable members of the community, and a vast majority of the bugs persist. So table 5, here we have cell counts and residuals. And you can see the difference here between the observed and the expected values. So the key diagnostics from this table is to observe the proximity of observed and expected responses. The residuals are the differences between the observed and the expected responses. So this is what we actually saw in nature, 10. And the expected response is 10.498. And you can see it for the different doses, the 4 levels of doses, and the impact it had on the number of subjects. The probability is the predicted probability of the observed response to the stimulus, so the likelihood of that outcome occurring. It's not the predicted proportion of the response to the stimulus. So table 6, here is the confidence limits. It's the probability that indicates the proportion of the objects responding to the stimulus, in other words, bugs being killed, and the estimate of the dose, which is the independent variable. Now, it's the value of the stimulus needed to achieve this proportion. And again, it's in the form of standard deviations. The calculation for the medium lethal dose 50% was calculated above. But you can see it, right here. Here's 50%. And we have a value of 3.7, which is in this range, in this sort of central range here, which we calculated above, 0.317, which fits here, right at the 0.5. All right, here the value is actually 3.151. Okay, so let's think of a different application of this model. We could there is a Probit response model for subgroup analysis. All right, so here the Probit procedure can make an analysis of a dosage level of different agents. So we can propose a model where we want to distinguish and establish how much of which insecticide or combination of insecticides, whether it's rotenone, diguelin, or a mixture of the two, that it takes to kill some insects. This procedure is identical to the Probit technique above, except for the following exceptions. A subgroup analysis requires that a nominal factor variable be inserted into the factor and its minimum and maximum values be identified on the data sheet, and that these be inserted. As well, the insertion of a factor requires a parallelism test. Right? This is like a collinearity test. So let's go run this model, this second model. So we go to Analyze, we go to Regression, we go to Probit, and again we're going to insert the NDED as the response frequency, the dependent variable, and observed as the other category of the dependent variable. We've dropped in dose as the covariate. We've made no transformation, but we're going to introduce agent as a factor, and we need to define the range of this, and it's going to be a 1 to a 4. And this captures the 4 categories of no agent, diguelin, rotenone, and 4 will be all the agents being used simultaneously. Okay, so we're going to click on the statistics. We're going to go up to options. And under statistics, we're going to make sure we have frequencies and fiducial confidence intervals, which is already there, as well as the relative median potency and a parallelism test, which is required for this type of test. And then we click continue and OK. So here are the results for the second model. Again, these models have been indicated as 1 to 8, but different versions of SPSS might change that. So we have here the Probit response, transformed responses. It's a scatter plot of the log dose in the x-axis and the Probit y-dependent variable on the y-axis. The relationship should indicate that each of the separately colored points should each demonstrate linearity for the Probit to generate unbiased estimates. In this case it is. If you see here we've got agent 1, 2, and 3. 1 is the first, 2 is the second, and 3rd is the combined dose. And we can see that, again, there's a rough linear estimate. And it's not, at least it's not curvilinear, which is what we're looking for. All of the gray, green, and blue dots indicate linear patterns between the 2 variables. And if not, we have to transform. And if you recall how to do the transformation, it's Analyze, Regression, Probit, and we would do then the transformation here, log base 10 or the natural log. But we're not going to do that. So if we go to table 3, up here we've got the parameter estimates, and now we've got 3 intercepts for the 3 different arrangement of doses. So we have the dose, 0.382, divided by the standard error, 0.063, gives us a z-score of 6, and we have a significant result. All right, so we can make predictions here because we know that there's no false positive, and so we can generalize from the sample to the population. So table 4, we have the Pearson goodness of fit test as well as the parallelism test that we added. So here we have 121 with a probability of 0. And if you recall, we have to apply the opposite interpretation here, and this indicates a poor fit of the model. All right, so the dosage just does not correlate strongly with the death of the insects. So there's a high probability of a false positive. Now, the parallelism test tests to see whether the 3 different insecticides can be distinguished from each other in their effects, and therefore whether the type of insecticide, rather than just the dose, can provide a better prediction of the outcome of the model. In other words, is it the amount of the agent or the type of agent? As with the Pearson chi-square test, the statistics should be interpreted in an opposite fashion, where a high value accompanied by a low significance indicates a poor fit. Now in this model, we have a chi-square of 4.896, a degree of freedom of 2, which is the one category of the dependent variable and the independent variable, and we have a significance which is higher than 0.05, which indicates that there is no parallelism, and that therefore the cases are distinguishable. Okay, we have table 5, the cell counts and the residuals, and we've got the three categories now of the agent, which are superimposed over the earlier values of the amount of the dose. And again, we're looking at the residual here and its probability, which is the difference between the observed and the expected response. Table 6 are the confidence limits, and they're broken down to include each of the probability ranges distinguished by the separate factors, which in this case are our agents. We've got agent 1, agent 2, and agent 3. Okay, table 7 is the relative median potency estimates, and these factor agent values are displayed for each combination of intersection of the other factors. So we've got the three types of agents interacting with each other, and it creates an estimate. So this is the Probit analysis.